So this video covers probably the most important derivative rule in all of calculus, and it's called the chain rule. And this rule is so important, it's in every single derivative that we've practiced already. It's just kind of been hidden, and it applies itself to more difficult derivatives. And so, I'm going to do my best to obviously go through it. But we're going to reinforce this in next week's videos when we cover some more derivatives of some different functions. But for now, we're just going to try and dive in. So as a reminder, the types of derivatives that we know how to take right now are either of essentially just a polynomial like x cubed or maybe 7x to the negative 23rd, right? We can take derivatives of things like this using the exponent rule. More generally, we can also take derivatives of things when we have some function plus another function, right? It's just the derivative of the first added to the derivative of the second. We know how to take the derivative of the product of two functions, right, via the product rule. So maybe up here I'll just write this as f prime plus g prime when we take the derivative, and that we're going to get, using the product rule, we're going to get f prime g plus f g prime if we take the derivative here. And then the last one that we covered was the quotient rule. The quotient rule looking, if we have the quotient of two functions and I take this derivative, we're going to use the low d high minus high d low all over low low. So it's going to be low d high, so times d of, we'll say f, low d high minus high d low all over low low, in this case g squared. And so we've tackled how to cover this, and this is most types of functions that we are going to encounter. And the last one that's kind of the most interesting is something that you encounter quite a lot, which is the composition of functions, right? What happens if we identify that I have one function inside of another function, right? Like, how do we do this derivative? And before I answer that question, I'd like to remind you, what does it mean to have the composition of two functions? So, for instance, to do it would be like if I tell you that f of x is equal to x cubed and g of x is equal to 2x plus 1, right? So then f of g of x, right? The way that we would do this is we would plug g of x, what we have for g of x, inside of our f of x function. So what we're really doing is f of 2x plus 1, and that 2x plus 1, we're going to plug in everywhere that we see an x inside the f of x function. So this would just be 2x plus 1 cubed, right? This is a composition of functions. And it may, this is something that we're going to have to practice, because if I started here and said, what two functions, kind of comprise this single function, right? We could think of this as one single function, but it's actually easier to identify it and say, well, there's kind of like an inside function, right? There's a 2x plus 1, and then, right, that was our g of x, and then there's an outside function, which is like all of that stuff cubed, and that was the x cubed part. So, similarly, maybe we'll use some different functions. So maybe we'll do one more. Let's let like f of x be equal to sine of x, and then g of x be equal to e to the x, right? So then maybe we'll do the other way this time. So g of f of x is going to equal, okay, so in this time we have f of x is on the inside, right? And so what we're going to have is we essentially have g of sine of x. And because we have this sine of x on the inside, that's going to go wherever I see an x in this g of x function, we're going to replace that with sine of x. And so that's going to give us e raised to the sine of x. And again here, right, you can identify the two parts, right? We have kind of like, we have our outside function, if you will, is going to be the e to the x bit. So this e raised to something, right? That was our g function. Right? That's this stuff. That's what was on the outside. And then the stuff that goes on the inside, our inside function for this composition would be sine of x. Okay? And so it's going to be really important for us to be able to identify these things kind of moving forward, because this is how we identify that we need to use the chain rule, right? When you look at a function and you go, wait a second, right? This thing is a composition of two functions happening at once, right? This is a composition of a polynomial and another polynomial. This one's a composition of a trig function, and then e raised to the x, e raised to some power, right? Once you realize that that's happening and you need to take a derivative, we are going to need to use the chain rule. And so to answer the question of, what does this derivative look like, I'll pop it right in here. So the derivative, once we take the derivative with respect to x or whatever our input variable is, what we're going to get is we do the derivative of the outside function. So we're going to do f prime of whatever the heck was on the inside in the first place. So the derivative of the outside function, and then we're going to multiply that result times the derivative of the inside function. And this is how we tackle taking the derivative of the composition of two functions. So this is what we call the chain rule. Now, I know in its very abstract and general form like this, it probably doesn't make too much sense. So let's go ahead and tackle the example here on the right. Let's tackle this one. So for example, right? I'm gonna say use the chain rule, although most problems will just say take the derivative, but use the chain rule to determine the derivative of 2x plus 1, and then all of that, let's say cubed. Let's pick a different color. Cubed. All right. Okay, so the derivative of that function there. Okay, so use the chain rule to determine this derivative. Okay, so the very first thing that we notice is that we have the composition of two functions, okay? And so what we're going to need to identify is what I'm going to call the outside function, our outside function, and what is going to be like our inside function, okay? Because the chain rule is, if we go back over here to the formula, it's the derivative of the outside function times the derivative of the inside function. And so we're gonna identify here that, look, the outside function from what we saw before, the outside function here is all of this stuff, whatever it is, cubed. And the inside function is just the 2x plus 1, right? It's 2x plus 1. It's that stuff, right? That is the stuff that's like on the inside here. And so all we need to do is to do the derivative of the outside times the derivative of the inside, right? And so what we're going to do here is that this stuff, right, even if I didn't know what was on the inside, right, if we're just paying attention to this outside function, something cubed, how do we take the derivative of this? Well, we learned about that in the exponent rule video, right? This just becomes 3 multiplied by all that stuff raised to the second power. Now, what goes in here? Well, it's the same thing that was already there, right? We don't touch it. It's the 2x plus 1. And this bit, this thing that we just did right here, this is the derivative of the outside function. And we leave, whatever was on the inside just goes on the inside, okay? So that's that part of the chain rule. Now, the derivative of the inside function is also not going to be too bad, right? So the derivative of the inside, this is our g prime of x, is going to be equal to just 2, right? There we go. And so it turns out that if we address this problem in its entirety, that if we have y is equal to 2x plus 1 cubed, right, then y prime, the first derivative here, is going to be 3 times all of that stuff squared. So, I'll write it down, just 2x plus 1. And then we're going to multiply this by the derivative of whatever is on the inside. In this case, it's just 2. And we can simplify this if you want, right? Because we have a 2 times 3, right? And so the final answer here would be 6 times 2x plus 1 squared. And there's our answer, right? There's our derivative. And just as a friendly reminder, we can't multiply this 6 inside because it's guarded by this exponent of 2. Right? Okay, so, right, that's the chain rule again, right? The chain rule's here. It's in the upper left-hand corner. It's the derivative of the outside times the derivative of the inside. So let's do another example, okay? Let's see here. So, for example, given y is equal to the square root of x to the 7th minus 5x squared, right? What is y prime? Okay, so this one's a little bit trickier in the sense that it doesn't look exactly like the same thing as what we had here on the right-hand side, right? If what we have here on the right-hand side, this 2x plus 3 cubed, we were able to identify an inside and an outside function. And, we're going to do the same thing for the one that's here on the left. So for this one that's on the left, we can kind of identify that our inside function, we can take a guess, is going to be the x to the 7th minus 5x squared bits. And our outside function is going to be that square root bit. Now, as a square root sign, right, this maybe makes a little bit less sense. So, we're going to use our mathematical proficiency and we're going to say, oh, wait, this is the same thing as x to the 7th minus 5x squared raised to the 1/2 power. And so our outside function, you can think about it like the square root, but it's better to kind of think about it as all of that stuff raised to the 1/2 power. So in order to use the chain rule here, again, the chain rule kind of maybe written out in English is the derivative, or maybe instead of writing out the word derivative, I'll just say it's the derivative of the outside function and then multiplied by the derivative of the inside function. And so here, right, if we tackle the derivative of the outside function, right, that's just going to be, we're going to take this and do what we do best, which is the exponent rule. We're going to have 1/2 multiplied by all whatever stuff is there, and then we subtract 1 from the exponent, which is going to give us a minus 1/2 exponent. That's not too bad. Now, what's on the inside of those parentheses? We keep whatever's on the inside, right? So we're not worried about it. We're just doing the derivative of the outside. And now let's do the derivative of the inside. So let's take this guy and do the derivative of the inside, which is going to be 7x to the 6th minus 10x. And I'll put that in parentheses there, because this is actually our final answer, right? So we're going to get y prime is equal to 1/2 multiplied by x to the 7th minus 5x squared raised to the negative 1/2 power, and then multiplied by 7x to the 6th minus 10x. Now, can we simplify this at all? We could tidy it up just a little bit if we identify, if we know what to do with our negative exponents, which we're going to get better at as we kind of proceed in this class, right? This is the same thing, right? How do you tackle a negative exponent? Well, that's the same thing as having 1 over, right, x to the 7th minus 5x squared raised to the positive 1/2 power. And then if you want at this point, positive 1/2 power is the same thing as a square root. So we could tidy up this entire answer and we could say, okay, so we have y prime is equal to, we're going to have this is going to stay on the top. So we have 7x to the 6th minus 10x divided by, we have the 2 from that 1/2 there, and then multiplied by the square root of x to the 7th minus 5x squared. And then, that's it. We're done. That is the derivative using the chain rule. Now, I had mentioned before that, the chain rule kind of has existed in everything that we've done so far. And let me just kind of show you, it's going to seem kind of silly, but let's kind of go as an example. Let's do, if y is equal to x cubed, right? Use the chain rule, right? Use the chain rule to get y prime, okay? So if we use the chain rule to get y prime, you might say, okay, well, we just have x cubed. We can just take this derivative, no problem. Which is it's true, right? And that's exactly what we're going to do. Let's identify an inside function and an outside function here. It's going to seem very silly, but let's do it anyways. Okay, so in here, I'm going to say that my outside function is going to be something raised to the third power. Okay, and my inside function in this case is just going to be x, right? It's kind of silly, but I could write this original problem in like parentheses x cubed, right? And I could take these derivatives. So let's do it. Let's use the chain rule. So according to the chain rule, it's going to be the derivative of the outside function, which means, we're going to take the derivative of this, which is going to be 3 times whatever the heck is on the inside, quantity squared. Great. And then we're going to multiply this by the derivative of the inside function. But the inside function is just x, right? So what's the derivative of x? Well, the derivative of x with respect to x, that's just 1, right? You could do the exponent rule, and you could say, okay, it's x to the first. We bring down 1, x to the 0. X to the 0 is 1. This is just going to equal 1. So our final answer here, if we were to go the long way and say, okay, so y prime is going to be 3x squared times the derivative of the inside function, which is just x, but this thing, that's just 1, right? This is just equal to 1. And so we get indeed still that our y prime is just equal to 3x squared. So the chain rule does exist. It just doesn't ruin our plans when it comes to doing, simpler rules like we had before, like the exponent rule. It doesn't change anything. Okay. As a comment, one thing that I'd like to point out when using the chain rule is sometimes, you may think it's easier to use a chain rule, and other times it, may not be easier to use a chain rule. So, for instance, if I were to give you, as an example, if I were to give you y is equal to x squared minus x, and I just gave you this and said, what's the derivative? You may recall that I could just as easily, I could say, wait, this is just x squared minus x times x squared minus x. I could multiply these together. I could FOIL them. So if we're very careful and we do, the first, which is x to the fourth, right, the outer, which is a minus x cubed, we're going to have another minus x cubed when we do these inners. So we're going to have a minus 2x cubed. And then, we have a plus x squared there. Well, so that just means that our function we're taking the derivative is this, so we could just do that y prime is equal to 4x cubed minus 6x squared plus 2x, and we're done, right? There's our derivative. We didn't even have to use a chain rule in the slightest. We could have used a chain rule though, right? If I go down the chain rule rabbit hole, right, that says that the derivative here is going to be, right, the outside function here is going to be all of this stuff squared, right? That's our outside function that we identify. So it's 2 times x squared minus x raised to the first power, and then times the derivative of the inside function, that inside function being x squared minus x. So this derivative, as a whole is just going to be 2 times x squared minus x, and then times the derivative of x squared minus x, which is going to be 2x minus 1. And we could FOIL this out just to, make sure that we actually did get the right thing. So again, we're going to have x squared multiplied by 2x. That's going to give us a 2x cubed. We're going to have x squared times minus 1 is a minus x squared. Then if we start doing the inside set, minus x times 2x is a minus 2x squared. And then times minus 1 is going to be a plus x. And then all of this is multiplied by the 2 that we have in front. And so we're going to get, for our answer, we're going to get 4x cubed. This becomes minus 3x squared, but then times this 2 is going to be a minus 6x squared. And then plus 2x. So it turns out that yes, indeed, we get the same exact answer. Which I think is I don't know, pretty nifty. And just to go one further, right? We could have also said, look, if y is equal to x squared minus x quantity squared, so times x squared minus x, I could do the product rule, right? We could have done the product rule in this particular case. We could have labeled this thing f. We could have labeled the other one g and said, I know what the product rule, right? The product rule is going to be f prime g plus f g prime. So off to the side, we're going to need f prime, which is 2x minus 1. We're going to need g prime also being 2x minus 1. And so once we have all of those, we just pop them into our equation. So we're going to get f prime, which is 2x minus 1, times g, which was x squared minus x, and then plus f, which is just x squared minus x, and then times g prime, which itself is 2x minus 1. A lot of repetition here. But, this is basically this is the same thing as, okay, well, since this first term is the same thing as this term, that means we have two of them, 2 times 2x minus 1 and times x squared minus x, which we already did, right? We tackled that. We know that this becomes this thing. So what we just got here is indeed going to FOIL out and be the exact same thing, right? You could do this to your heart's content. And as the problems kind of progress, you're going to need to use, the rules a little bit together. For instance, if you have something that's really, really strange looking, like maybe we have like x squared minus x multiplied by x plus 3 raised to the 10th power, and then we're dividing this by 2x minus 1, all of a sudden, we could say, okay, well, the first thing that comes to mind maybe is to try the quotient rule. So this is like the high, this is the low. But I know at some point in the quotient rule, I'm going to need to take the derivative of the high part. And if we isolate this on, on our own over here, there's going to be a product rule. Right, we're going to need a product rule for the top here, and then in doing the product rule, right, if this first thing is f and the second one is g, right, at some point I'm going to need g prime, and that means to take the derivative of this, I'm going to need the chain rule, right? It's all going to start kind of stacking together, and sometimes these problems are going to feel like they're a little bit long until you really start getting the hang of it and kind of going on autopilot, and then they kind of all just kind of blend together pretty well. Okay, so now you may notice, just as a final note, that in this video I did not cover, for instance, the example where I said, okay, how do you take the derivative of e raised to the sine of x, right? And we haven't really covered functions, right, like e to the x or tangent of x or the natural log of x or maybe some inverse trig functions like sine inverse, or maybe if you haven't seen it like that, you've seen it as arc sine of x, things like that. And we're going to tackle those in the upcoming videos. But for right now, this very first week is just getting comfortable with these derivative rules, using polynomial functions that are not too bad, that we can kind of build some repetition, build some good habits with. And then in the next videos, you're going to start seeing us kind of dive into these. So hopefully this was interesting, and the chain rule it's a little bit of a mess right when you first start, but it's not too bad. And if you want, go practice some examples is always something that I encourage. If you have questions, shoot me an email, and if they're available and you're ready, then head on to the next ones.